Okay, now let's look at this problem. So, I mean, fundamentally, this is a mass transfer problem. So we have a uh, source of uh, chemical species A. In this case, it's pathogen, which is um, moving away from the point source. Um, and what we need to know is if we can solve concentration of A, say A as a function of space and time, then we can basically, and if EPA's requirement for pathogen safety level of pathogen is CT, that's kind of a threshold. We just need to determine, the radius of such a cylinder in which outside of this cylinder, the outside of this cylinder, the concentration of A is below the threshold, right? The safety threshold, right? So this is a mass transfer problem. So the site can be considered as a point source as for the toxic gas, because if you look at the length of the train, it's 25 meters, and the distance between cities are at least 5 miles, which is 8,000 meters. And the ratio of the length of the train divided by the distance of between cities is 0.003. That's much smaller than 1, which means that in this problem we can assume the point source, the source of the toxic gas is a point source, and we want to solve the mass transfer in this region, in this blue region, right? The red one is a point source, which gives out the pathogen that is moving away from the point source in the radial direction. And there's no reaction in this region. If we assume there's no flow, right, that's only true if there's no wind, right? So that's kind of the simplest case we can solve by hand. So we will study that. But in real situation, there's always going to be wind. In that scenario, you have to use a computer to solve this problem numerically. But conceptually, let's just consider the simplest case. We have a binary mixture that is air with phosgene, and we have constant C that is valid if we have ideal gas assumption, and then we have constant diffusivity. And in this case, let's consider a 1D problem in a cylindrical coordinate, right? So we only care about the radial direction mass transport near ground. We ignore the vertical direction mass transport, right? That's a big assumption, but to simplify the problem, let's do this. Then in this case, we are looking at basically a mass transfer problem in this cylindric coordinate. Then because there's no reaction and there's no flow, and we can use Fick's second law, right? We can write down this equation in which A is a phosgene, B is air, and to solve this problem, this is ordinary partial differential equation. We need one initial and two boundary conditions, and the initial condition is that throughout the whole the region here, the concentration of A is 0, and the boundary condition is at infinity, Ca is 0, and at the point source, at R equals 0, the concentration of A is known, which is Ca now, right? So at first glance, we can solve this problem as using Fick's second law as a mass transfer problem, simple mass transfer problem by with these two boundary conditions and the initial conditions. But now if you look carefully, we find out actually as the phosgene is leaving the point source, the concentration at the origin is actually going down, which means Ca naught is a function of time. So it's not a constant. So then that means we cannot use this boundary condition, right? The boundary condition is changing. That just make it hard, right? So we cannot solve this, partial differential equation with only one boundary condition. Okay. Now, in order to solve this problem, we have to make further assumption, right? Now, if we make a steady state assumption, right? Let's say we don't care about how at any time, let's say the concentration profile is just not changing. And that will just simplify this problem to be similar to the two-ball problem we have solved, where we have a point source of species A, and then the species A is leaving the left bulb through a tube, right, into in this case, infinite volume, with a distance of r, right? The channel has a distance of r. In this case, V2 is much larger than V1, right? And to solve this problem, then we can assume steady state assumption. That means in this channel, the concentration profile does not depend on time. It only depends on the XA at left and XA at right, and the radius, right? So here the radius is infinite, right? And well, then with that assumption, with steady state assumption, we can solve CA as a function of R, right? And then we can solve, once we know CA as a function of R, we can solve for NA as a function of R, right? Now we can write down the mole balance equation for the point source of A, right? That's the left bulb in which we contains a given amount of pathogen, right? Let's say if that's Na. Let's say the moles of pathogen at the point source of Na. Then we have dNA over dt equals minus Na naught 0 AC naught AC 0, right? So here Na is a flux, just next to the point source, and AC is basically the area for the diffusive flux to happen, to pass through, right? And here we can take out C and V1, we can get this equation. And we know Na is at R equals 0, Na becomes only a function of XA, right? So now you have an equation, ordinary differential equation you can solve. It's an ordinary differential equation of XA. Okay. So, and we've solved the similar problem for a 1D tube in Cartesian coordinate, in which when we make steady state assumption for the diffusion in the channel, right, that gives us the concentration of A in the channel to be independent of time, right? But it's dependent on the coordinate, the space, and it's linearly dependent on the location. It's a linear function of the location, and similarly we can get NA. If once we know CA, then you can use Fick's first law to solve NA. That gives you, it's a constant and it's proportional to XA over L, right? In this case, because XA in V2 is 0. So this is XA in V1. Right, then you can just, plug NA into the mole balance equation that give you this equation, right? Then this is ordinary we've solved this ordinary differential equation in our homework problem. Okay, so this just to let you know, conceptually we can solve this problem. If you solve XA as a function of time, then you can solve CA as a function of radius and time, and NA as a function of radius and time. Then you can determine at a certain radius, the concentration of A will be lower than the threshold, safety threshold. Okay. So obviously this is only conceptually to help you to understand how to apply the knowledge you have learned to solve a problem of this kind. But this problem will not appear in our exam because we are not gonna ask you to solve a mass transfer problem in in a cylindrical or spherical coordinate. That's too much mess. Okay, now problem 4, we're going to revisit the bigger problem, right? So in the class we talk about the bigger problem, but very briefly. So some students are kind of having a hard time to kind of understand some of the equations. Now we're going to revisit this bigger problem with a background, and we're going to do this step by step, right? So now the background is that in real life, the beaker problem is very common. For example, if you leave a cup of water in the room, and given time, the water will evaporate as water molecules are leaving the liquid phase and get into the air. And we may ask how long it takes for the cup to dry out, right? So in order to, here is basically a kind of a schematic of this problem where we have a beaker and we have water, right, at this level. And so outside the mouth of the beaker or the cup, we have air, assuming the air is circulating very well. Then we have no water vapor here, right? So this is outside the cup, we have pure phase B. In the liquid phase of water, we have pure phase of A. It's only the region in between we have a mixture of A and B, right? So we have a mixture of the vapor of water with air, okay? And water is evaporating, so it's leaving the liquid phase. It's leaving the liquid water, and leaving the water in this direction, and eventually it's gonna enter the air. Meanwhile, air is trying to, because there's a concentration gradient here, air is also gonna be diffused downward into the water, right? So that gives you the direction of the max flux of water and max flux of air. So in order to solve this problem, in order to figure out how long it takes for the cup to dry out, we can apply mole balance equation to the liquid phase of water, right? So if you draw a control volume that basically encapsulating all the liquid water. So, and we can write down the mole balance equation. dNA dt, Na is the total amount of water in the liquid phase. That will be equal to the net inflow, right? In this case, because water is evaporating, so net inflow is negative. So we have negative Na. Na is the flux of water vapor leaving this interface, multiplied by AC, which is a cross-sectional area of the cup, right? If you solve this equation, you can get Na as a function of T. Then you can, if you let Na T equals 0, that gives you the time it takes for the cup to dry out, right? So essentially, in order to solve this problem, we kind of need to figure out this ordinary differential equation, right? So here AC is a constant, right? And Na, both Na and NDA, Na, like lowercase Na, the mole fraction, the moles of A, and uppercase of A, that's the flux of A leaving the water phase. These two are unknown variables. In order to solve this ordinary differential equation, we need to find out how Na is related to, lowercase Na is related to the uppercase of Na, right? So to solve this problem, let's look at, in order to solve for Na, right, the flux of A leaving the liquid water, let's look at the region in between air and liquid water, right? That's the region the region in between, which is a mixture of A and B. We apply the mole balance equation to this region. So that's the integral mole balance equation, right? Now, if we make steady state assumption that dc over dt in this region is 0, and there's no reaction in this region, then that will simplify this equation to only this term. That's the flux term. Now, that is integral of the of the outward flux of Na leaving the control volume multiplied by the by the a vector, which is the unit vector pointing outward. That is perpendicular to the control volume, but pointing outward, right? So to further break down this integral, we need to look at the control volume, its a vector, as well as the direction of the the mole flux of A. So that is control volume here, right? So the control volume is just this region again, the region in between the air outside the beaker or the cup and the liquid water, right? So, and when the water vapor is leaving the water gas phase, right? So it's pointing upward here, the direction of the flux. And then it's also pointing upward at the mouth of the beaker. And there's no flux at the wall of the cup or beaker, right? Then the A vector, the direction of the A vector in the four surfaces of the control volume are all pointing out, right? So now with that, we can just, plug in all the information into this equation. We can simplify it because there's no flux in the left and right surface, so we don't have to consider them. Then there's only the top and bottom surface. If we define a coordinate to be this, where the origin is at the mouth of the beaker, pointing downward, and at the liquid, the liquid gas interface is at a location of z equals L, right? So at the mouth of the beaker, we have the A vector to have the same direction of the flux. So that gives us a positive NA, right? The dot product is basically NA. Then at the bottom of this control volume, because the direction of A vector is opposite of NA, so we have minus NA, right, at Z equals L, right? That's our definition, right? That's our definition for the coordinate. Z equals L is where the liquid vapor interface is located, right? So then that gives us NA at Z equals 0 to be the same as NA at Z equals L. In this case, because the control volume can be arbitrary, right? We can pick a control volume where the bottom surface is overlapping with the vapor water interface. We can also pick a bottom surface to be like halfway through this control volume, right? And we're going to get the same conclusion that just suggests NA is a constant everywhere throughout the Z, right? For Z equals from 0 to L. And by the same token, you can do the same analysis for NB. You will find out NB is also a constant, and it equals NB at Z equals L.
里面了，看你外面的吧，我看你外面的爸爸。